this is a good time for the webinar to start. So thank you, Guanning, for signing up to be the speaker for the webinar. At the first, I'd like to use around 3 minutes to introduce the SZ4D and SZ4Grads, and then I will give a very brief introduction to Guanning, and then we can start. SZ4D stands for subduction zone in 4 dimensions. We are here to understand the limits and possibilities of predicting subduction zone geohazards. SZ4Grads is under the umbrella of SZ4D. This is a collaborative, interdisciplinary, and intercultural network for graduate students and recent graduates studying subduction zone processes. During the webinar, we got live translated closed captions. You can find a button at the bottom of your screen. And we also will record this webinar and we will upload it to YouTube for you to catch up later. Please try to fill out this demographics survey at the start. I'm posting this into the chat. This is very important for us to improve everything during this seminar. And also this webinar will be 45 or 50 minutes long. We are also, oh no, let me post the link to the survey. And also SZ4D is currently hosting a student exchange program with Chile. So basically you can go to Chile for a month to like learn about everything, and your advisor don't have to pay for anything. Basically, please feel free to sign up for this. And Guanning Pan is currently a postdoc at Cornell University under the supervision of Jeff Abers. He graduated from University of Utah in 2021, and also he got his bachelor's degree from University of Science and Technology of China in 2015. Today, his talk will be about focusing effects of the teleseismic wave fields by the subducting plate, evidence for continuous Juan de Fuca slab. Thank you so much, and this is your time. Thank you.
Thank you, and thank you for having me here. And today I'm going to talking about a little bit focus a bit on the Wavefield and how to use it to construct the structure on the Fuca slab. And you can see the beautiful background here is the coastal range caused by the subduction of the Fuca slab. And normally like seismic imaging is a really powerful tool to image the subsurface structure of our Earth. And the really traditional or like really common use in the seismic imaging is the travel time information of the seismic waves. You can see from this figure, when the seismic wave travels through the different structure, it arrives at the seismic station at different times. We can use these times to get information or like the seismic velocities of the subsurface. However, you can see from here, this is seismic waveforms really wrong. It has a lot of information, not only the seismic body wave travel times. You can see only like its amplitudes could carry a lot of information about the subsurface structure either. Normally, like we have seismic amplitudes can be affected by a lot of issues, like if due to the seismic velocity, it has multipassing, scattering, or geometry spreading. But it just all these are still in elastic properties. Also, another like a factor can affect the seismic amplitude is an elastic, which we call it attenuation, which means the seismic wave energy can transfer to heat and lose its amplitude. And what is multipassing? Multipassing from this cartoon, you can see like if you have some seismic anomalies like these high velocity seismic anomalies, then you can see like the paths of the seismic wave is slightly different to what you expect. And this will cause some sort of like amplitude, like if you're adding like a lens effect, then we'll focus some energy on some region, resulting in a high amplitude. And the other region, for sure, it less energy focus. It has like smaller amplitudes. So like normally like the amplitude effect at long periods are really small, which means when you observe like really large variations at long period data, it means like the heterogeneity or velocity anomalies will be stronger than you expect. Like for example, in Jan all 2014, you can observe like the amplitude variations in the P wave and F wave, like not only the amplitude but also the waveform durations changes along like the ranges, and then use it to imaging a faster slab structure beneath opposite. So here I'm going to look at the amplitudes, the seismic amplitude variations in Castadia regions and see what it can tell us about the structure of the Castadia. So like Castadia subduction zone is span like from northern Vancouver to California. So it's caused by subducting the Fuca plate subducting beneath. So like it generate a arc with really 10 high hazards volcanoes along the arc. And also it has capabilities to generate really large like magnitude 9 earthquakes in the region. You probably already know that like there's a new Castadia region earthquake center was founded to just investigate the hazard in the regions. And Castadia is a really special subduction zone all over the world because like it's famous on its low level of seismicities. So here's our two maps. The left map showing the crustal seismicities with the color marks the seismic densities in log 10 scale, like per kilometer square and per year. You can see like these numbers are pretty low, and it has really strong like regional features like the middle near Mount St. Helens. All these volcano regions are much less seismicities, and the right map here shows the intra-slab, which the earthquake happened inside the subducting slab. You can see it's much fewer seismicities, and it has stronger spatial, like focusing space on regions even more than the crustal. And because it is so few of seismicities, so we lack of like local body waves to study the structure of the region, like the not just velocity structure, but also the attenuation structure has been like really not well studied and not well understood. And most imaging results from the regions, like one big part rely on the surface wave tomography. You can see like it can be either use the distant earthquakes, the radio wave from distant earthquakes, or use the ocean storm generate ambient noise field to do the surface wave tomography. But like as the map show on the right here is the topography results from different studies using similar signals but different techniques. You can see like these results kind of inconsistent. For sure, you can see some common feature, but if you look at the whole thing, it's kind of inconsistent. And another tool could be used the teleseismic body wave, as shown on the left figure here is the shear wave structure using the teleseismic body as well. You can see a really high velocity subducting plate here at 80 kilometer, but then on down to 150 kilometer on the region, 44 degree to 46 degree, the high velocity anomalies disappeared. Again, like although another techniques use the receiver functions, like look at the P to S converted wave, but similar, you can see like 44 degree to 46 degree, it seems like the convertive wave phase here is disappear. Like the D prime is the profile along the north-south. So you can see like similar disappear. So like somebody argue that this disappears some kind of like artifact of tomography, but also somebody believe this is real, and then they propose that maybe the subducting plate is here or has a gap or hole inside the region. And this gap or hole is kind of a source of magma of the whole Cascadia arc. So here, so in this study, I'm going to use the IMUS data and use the teleseismic body weight to see what we can learn to the region. The IMUS array is a dense seismic broadband arrays deployed in 2014 to 2016, primarily used to imaging the magma beneath St. Helens. It composed like 17 broadband seismometers in spacing at 10 kilometers. So it's pretty dense for the region. In this study, I'm going to use the teleseismic or the distant earthquakes with magnitude large or equal to than 6. Mostly, I only use distance as 30 degrees to 70 degrees, but I scale the distance up to 90 degrees to southwest, try to pad azimuthal gap here. So first, I want to see if we can see anything exciting in the amplitude in here. In first case, I'm going to show you for an earthquake located on the northeast, which the seismic wave travel from northeast to the our arrays. Here are some examples of some seismic waveforms. The red waveforms is a teleseismic waveform and transverse component, and the red waveforms is a station kind of located at east. And the blue waveform is station 1 located at the far west. You can clearly see that when I filter the waveform on the 22nd period of 0.05 Hertz, there's a really large amplitude variations near like 70% of like amplitude variations on these two waveforms. And if we look at the whole seismic arrays, we can see the pattern of waveform decreasing from southeast to northwest, which we don't really expect to observe on this kind of only 100 kilometer scale, because you can imagine a 20-second waveform, the period, the wavelength of the waveform is close 100, and then it has such big amplitude variations, which is not unexpected. And then if we look at on the earthquake, a similar earthquake located at east, we can observe similar like larger amplitude on the east of modern St. Helens and smaller amplitudes on the west here. But if for another earthquake located on the other side, like here is from Alaska, then travel the earthquake seismic wave travel to an array from the northwest, which means when it comes to the array is along to the downward direction of our slab. Then you can see like the amplitude variation is kind of small. It's only 10%, is close to yellow. And what could cause this phenomena? Oh, sorry. And if we look at more earthquakes located at like different azimuths, you can see like primary, if the earthquake is like located at the east, it can see a large amplitude variations. But when the earthquake comes into like some sort of west, the amplitude variation is relatively small. And what could cause these phenomena? Like I mentioned before, like there's two ways could generate amplitude variations. One is focusing, another is the attenuation. Normally for attenuations, normally like the background has like lower Q because it's hotter, and so it means much stronger attenuations, which means if the attenuation is the origin of these amplitude variations, the seismic station located on the east of Mount Heron will consistently lower to the west of our Mount Heron. It should not has anything to do with the incident angle of our seismic wave. And besides, for this period on 20 seconds, even for your low Q on here, the amplitude variation, it should be just only 10%, not enough 10%. It could be not like what we observe large as like 70 or 100%. So another case possibilities would be the focus effect by the high-speed subducting plate itself. That like I showed the picture because the high-speed subducting slab act as a lens, then we can focus the energy to one region, and the other region will have less energy and then smaller amplitudes. So to verify or test if this is the case, here I'm going to use the 2D to do some waveform modeling to see if we can generate our observation. Because like the Castadia is kind of a perfect two-dimensional structure, so I just take a slice from the subducting plate here and use do the two-dimensional calculations. In here, AA prime is showing on this map here. So in here, I just started from a Lewis symbol subducting model with velocity increase at about like 57%. And the thickness of our model is about 35 kilometer. Is based on the 8 to 10 million years thermal age of our subducting slab. So here is a map showing. Here is a video to show our waveform propagation here. You can see like the instant is a plane wave assumption, which is almost good for the teleseismic wave. And the instant angle is 25 degrees. It's also a good approximations for the teleseismic at the distance at like 50 degrees. So we can see for the seismic wave, for the seismic wave like travel up. For the seismic travel along the surface, you can see like the wave field has bended because of the high velocity. So this bended will cause the waveform recorded difference in amplitudes at different stations in our regions. So if we look at a waveform case, or in some videos, in this case, the seismic wave field is like injected from the east of our model, so it equivalent to our earthquake circle here. Then the seismic wave travel along the west. Then the seismic wave travel along the up dip direction. And if we look at our synthetic wave field here, these are the same waveform as station 1 and station 2 marked at the map here, and use the same filter I did to the observation. The red is station 2 located on the east. You can see it clearly. It has larger seismic amplitudes than the blue wave field, which is the station 1 located on the west. And then if we look at the whole seismic arrays, the blue stars are the seismic amplitudes recorded across the whole image and then projected to the AA prime profile here. And the red circle is our simulations. You can see it's so similar. Amplitude variations, even the slope of these variations are really almost the same. Then if we look at another directions, like say like the incident wave field is coming from to the lab, which equivalent to our location located to the Alaska and injected to our array from the northwest. You can see in our synthetic waveforms for the same earthquake, there's really no amplitude variations or amplitude changes. And then similar, if we look at the whole array, the blue star again are our observations for these earthquakes located on Alaska, and the red dots are synthetic. You can see they are almost similar, and the variation is really minor at this 20-second seismic period. So here it seems like the focus is affect itself by the subducting plate high speed. It's kind of the reasons why these 20-second X wave can have such azimuthal dependent seismic amplitude variations. We also test in a more realistic seismic tomographies generate from thermal models, but we noticed that in these models, the velocity anomalies in the subduction slab is much more smooth. Maybe it's only 5%, 8%. We can see a little bit like similar amplitude change pattern, but it is much bigger. As I mentioned, because this model, it doesn't have really kind of sharp boundaries, so maybe that's the issue, like the sharp boundary can suggest the focusing. Another issue, it could tell us that at least 15% velocity variation exists in Cascadia is needed to generate such big velocity variations. So like I mentioned before, like another factor can affect the seismic amplitude is the attenuations. Attenuation is really important to subduction studies because it has so much sensitivity to the partial melt present. But like, how does these focusing effects affect our attenuation measurements? Because they both affect the amplitudes. So here I'm going to measure the differential attenuations from observation to explore their relationships. In seismic attenuations, you can see here is this. It is for sure it affect the higher frequency more than the lower frequency. Their relationships kind of exponential. So if we take a lot in a amplitude spectrum, you can see there's kind of a linear. So we can define the slope of this line as a T star, then it is the total effect of the attenuations along the whole ray path. Then we can take the two nearby stations from the same earthquakes. Then we can know the differential attenuations beneath for the regions beneath the right beneath the seismic stations. Here I'm going to use the multi-narrow band filter techniques, which I just used a series of really narrow filter. You can see as the figure shown on the left here, this is an example of the narrow filter I use. Each filter are really narrow band. And for each filter, I can measure an amplitude. Then I can also for sure the phase shape is related to the attenuation either. Then you can see from the amplitude spectrum is kind of like what I saw in the log 10 scale is kind of a linear. Then we can estimate the differential attenuations. This is the differential attenuation I observed from the image. For figure A is the measurement from the earthquake located on the east of our image. The red arrow, you can see the wave field propagation direction. And for figure B is the western earthquakes. Then you can see from the arrow, the seismic wave is going from northwest to southeast. Then you can see the result is some sort different when the seismic wave incident at different azimuths, which we should not expect. Like you only have one attenuation structure because most inherent. So like you should expect the same thing using different stations. But now here, like you can see some sort of azimuth complex. Why? So like so if we look at our synthetic again, in previous, I only show in one period, in 20-second periods, and has large amplitudes. But then also you look at the amplitude spectrums of our synthetic wave fields. In here, each line is on a station. You can see in this broad range of frequency, it has different effects on our amplitudes. It's solely from our high-speed subducting plane. And if we plot the amplitude spectrum like I showed before, you can see the amplitude effect from focusing. It is really high similar, or even call identical to the attenuation effect from intrinsic attenuations, which means the focusing by the slab can affect the amplitude in the way of our attenuation, which could cause some artifact in our attenuation measurement. So if we look at more like, but another thing is that like I saw before, the focusing has the azimuth dependence. So like how much it can affect your amplitude, it depends like which direction the seismic coming in. So in here case, AB shows the focusing effect generated by the eastern back azimuth. You can see we can measure a really large T star from this direction, like along the update of our slab. But in another back azimuth, the effect is minor, almost zero. So like, and so you can see like first the focusing in is so really complex azimuth patterns, which is different from attenuation. Another big thing you should notice here is like the T star we observe from the focusing effect are different from the amplitude and from phase. They are inconsistent. This is also different from attenuation either. If it is just caused by the intrinsic attenuation, all these terms, all these figures, you will expect the same values. That because all this difference, it gives us a chance try to isolate the focusing effect from the intrinsic attenuation measurement. Then we can move along to do the interpretation of our attenuation. Yeah, you can see this is more like measurement from the synthetic waveforms. You can see like still you can see the strong azimuth dependence, and then larger effect or larger T star measure from the phase data than the amplitude. And then you can see like at least 20% of the apparent differential attenuation is kind of from the focusing itself, not the intrinsic attenuation. So next thing I'm trying to look at like if like there's any multi-parting effect either. which means it's like any energies coming from slightly different direction. The technique I use to observe multipassing is the array pinpointing techniques. So the array is like, then it can give you the direction, the ray parameter and back azimuth of your seismic incoming seismic images. When you get into a right direction and right ray parameter, you will expect maximum amplitudes in your spectrum of slowness spectrum here. So in our case, I look at first for similar. I look at one earthquake locate our east first. First, I take a first 25 window on the really first 25 second window of our S wave. Then I got the slowness and back azimuth of this incoming energy. Then I take another 25 second window later. You can see from this eastern earthquakes, it has some sort of difference in incoming slowness. It rotates about 55 degrees, which means these later signals are coming to our seismic array in a slightly different directions. Or if I can use the sliding windows, which means I take a window and then move it from the beginning to the end. And for each window, I calculate one slowness. You can see in this case, there's a big slowness change along this teleseismic waveforms as well as the back azimuth. So like this is consistent with our amplitude variations for the eastern earthquakes, so really strong amplitude changes. But then similar, if you look at an earthquake locate on the northwest, which locate on the Alaska, similar thing, but then you can see the slowness, it doesn't change at all. And then if you look at sliding window and for the slowness and back azimuth, it remains almost the same, which also like similar to our amplitude variations, no amplitude change for those western earthquakes. So in this case, you can tell like, yes, it is like the subducting high-speed slab generate these multipassing and focusing effects. And from these multipassing and focusing effects, we can tell the subducting plate at least has 10% to 50% high velocity anomalies. And these focusing effect and subducting effect could like affect our intrinsic attenuation measurements at like at least 20%. Then we can try to expand this study a little bit from instead of just owning a region to see the whole structure of Cascadia. If we recall what I mentioned before, in all these teleseismic body weight travel time imaging, the pros, there's the high speed subducting slab disappears at 150 kilometer and propose a gap of our subducting slab here. So if there's a gap, like what they propose, the high-speed subducting slab disappears at 150-ish. So in this case, what was that? As you can see here, if any gap or tear present in the subducting slab, this kind of amplitude variation will disappear either. You can tell the blue dot here is our observation and the red dot here is the simulation based on the model I saw on the lab here. You can tell if any gap preserved, the amplitude variation will just disappear. But is that the case in the Cascadia? So I look at as many stations as possible along the whole Cascadia arc. Similar, I look at like earthquakes at two directions either. You can see from those earthquakes northwest, almost no seismic variations. But for those earthquake located on the east, you can still see there's a big amplitudes variations exist along the whole arc. This figure on the right left here is making more clear, like see for those earthquakes located on the east, there's a big amplitude changes. Then which means, is there a hole? Especially on their regions, you can still see a really large amplitude variations, which prefer there's no hole, which means like the slab, the Fuca slab maybe is continuous, not like what the travel type tomography proposed, like there's a hole, maybe there's no hole. So here is some of take-home point about today's talk. First, we observe the large amplitude variations and 20-second periods teleseismic wave as shown on the figure here. And these amplitude variations are caused by the focusing of the high speed subducting slab, Fuca slab. And this focusing effect could cause at least 20% of apparent differential attenuations, which means any attenuation results, if you want to make a useful interpretation, you need to correct focusing effect first. Last, it seems like the subducting plate beneath Castadia is kind of continuous from the Canada to North California. So happy to taking any questions now here.
Sorry. Thank you. Because this is going to be recorded, so can I read the questions and then I can also give you some time to answer the question.
Yes.
So the first question is from Juan. Great work. Can this method provide better constraints for the geometry of the slab? For example, dip?
Yeah, ideally it could, because like there has been studies like amplitudes could provide additional constraints to these geometries and amplitudes of anomalies. But like in that case, you may need a little bit more like a denser array and maybe more kind of inversion technique, not just like forward modeling. In our case, we just try to seeking potential answers, not to try to fight to the best answers. But like in this case, if you want to better constraints, it need to be like more kind of make it more going further to do use the amplitude information to do the inversion. And for sure, use the amplitude information and different frequency band either. Yeah. And I saw there's some questions on the chat either. You want to ask the repeat it?
Yeah, so thank you. So there is another question from Hao. Is the site response considered when marrying delta T star? Will it affect the interpretations regarding attenuation and focusing? Any idea to remove the focusing effect from the apparent differential attenuation?
Yeah, the site response in here is a good question. In the Cascada region here, we didn't see really big side response, because like the side response will similar to the intrinsic attenuation. It should not be the azimuthal dependent, which like if you see the azimuthal dependence like that, you can tell it is like not the side response is not that kind of case. But we do see some sort of side response on Alaska regions, which I haven't tried to see how to deal with that yet. But yeah, side response could affect attenuation. definitely. But in our case, because we didn't see it, I don't try to see how to deal with that. And any idea about the remove focusing? I haven't really do yet, but I think Zach on UCSB, he's adding these on his attenuation code to try to do that, because like you can see from focusing effect is solely strong azimuthal dependence. That is the way to do so, like try to compare observations from different azimuths and then try to identify if any focusing effect there. And I'm not doing that now, but Zach and UCSB, I think he's doing that, trying to update his code, and I hope the code could be available soon. Yeah. Okay. Any other questions?
Thank you. I also have a question. I'm also
Yeah.
doing attenuation. But,
Oh, yeah.
Is there a way to constrain the absolute focusing values?
Well, this is a good question and tough question either. Because like it's hard to define absolute value, right? Because like even though I just call focusing here, but actually when people always call focusing and defocusing, which in the term itself it is a relative term here. So like if like you be going back either this figure or like either we can just use the figure here. Like you can see like when we talk about it, the focusing and defocusing is always together, because like for the energy in slab here, it always need to be conservative, which means like this region have large amplitudes. Naturally, another region should have a smaller amplitude. The nature of this term has already means these are the relative case. So yeah, when like it is hard to define what's the absolute value here you are mentioning. So yeah, but the point is like although it is a relative case when you look at the whole region, but it has effect on your absolute attenuation imaging. So yeah, like it is hard, it's difficult to deal with that, especially in a single case. So, but like if you have a lot of earthquakes cover different regions, it has a better chance to try to disease effect out. So yes, in that case, or in the future, when the computer power is big enough, when you do the attenuation tomography, you can do the full waveform sense. In that case, we will naturally account on this effect of structure. In that case, you don't have to worry about it because you invert the whole thing together. And I know Ibru on Cornell Mine, she's doing similar job too, but it is a global scale, like to do the waveform inversion, but also consider the attenuation, like they coding the attenuation together. So in that case, you invert the attenuation and the velocity together, you get the same thing together. Then you don't have to worry too much, I assume. Yeah.
Sounds really cool. Seems that we have another question from Siyuan Zhang. Thanks for the great talk. The teleseismic body wave tomography and receiver functions should be affected by shorter wavelength structure. Do you have any ideas about a interpretation, including previous results together? What factor can be distributed in a much broader region, absent from previous studies, but influencing your focusing effect?
Yeah, like it is there's a interest comparisons like between among these studies. Like for the study I show, you can see there's a much weaker velocity variation at the custodial plane. But then you can see if like there's other studies using kind of waveform techniques, they got a much stronger velocities, like 20% or even higher velocities anomalies. So what I got here is kind of between. So the idea here is that like, yes, even body weight tomography receiver functions should be affected by not just shorter wavelengths, it affected by the wavelengths I see here. So like, especially for the body weight tomography, somehow it could be like due to the normalization or like the smoothing. And then like the final tomography results always underestimate the amplitude of anomalies. So, and for the receiver functions, we know almost like receiver functions are assumed in a like some sort of surface, right? But the point is like when you look at a more like the single body scattering case, in that case, the focusing or like waveform hearing this effect is kind of really a big deal. So like, yeah, like what I'm studying now, like the magma case, you can see when you have a really finite size of body, when it could have a really appearance focusing effects or like waveform hearing effects on the receiver functions either. So yes, in that case, if you think about in a finite wavelength case, these focusing effects actually really matters. For sure, if you just look at the ray series, in that case, the ray series may not stand. So yes, so I would say we need to consider more on like final frequency seems not just larger than the ray series case, especially when you are looking on some really finite wavelength bodies or finite size bodies. Yeah. Questions?
Oh, thank you. This is really a great talk. Thank you again.
Yeah, sure. Yeah. Yeah, thank you for having me here. And yeah, any questions?
Wait for
If
one
not,
more second. And at the end, I still want to advertise our exchange program between US and Chile. So if you're interested, please sign up. And thank you all thank you everybody for being here. And thank you, Guanning.
Yeah.
See you next
Yeah,
week.
thank you. Yes, you. Bye.
Bye.